All right, so we are starting today with actually a review from where we were last time. So we've got two questions that we want to cover. What I'm looking for here is the net ionic equation. So can you give me the net ionic equation for this reaction between lead-2 nitrate and sodium iodide? Now, formatting, don't worry about the formatting. Just do your best to put it in. All right, so one thing to keep in mind here, we're looking for the net ionic equation. Now to get there, we might have to do the ionic equation along the way. So as we're going here, we would need to go through the process. So lead-2 nitrate, that's going to be soluble because nitrates are soluble. Sodium iodide, that's going to be soluble because sodium ions are soluble. Sodium nitrate, soluble also. Sodium and nitrate are always soluble. The lead 2 iodide, remember iodide follows the same rules as chloride. So usually soluble except for mercury, lead, silver. So lead would qualify in that one. This is an insoluble substance. Your next step would have been to convert the molecular equation into an ionic equation. So everything that is soluble splits apart. And the insoluble lead 2 iodide stays together. We cross out the spectator ions, the sodiums and the nitrates. Those are common on both sides. What's left is lead ion, 2 iodide ions to make the lead 2 iodide. So that would be my net ionic equation. That's what I have to enter here. So to do the process here and to do it correctly, you kind of have to go through the whole thing. And ultimately, kind of the thing I saw as I was walking around was some of you just kind of copied the top equation down, or you started to put in the complete ionic equation, and that's fine, but just understand what's being asked of you. What you're being asked to do here was to do the net ionic. So we had to break it down that one extra step further. Any questions about this example before we move on to the next one? All right, I will take that silence as a no. All right, let's try this one on. We've got sodium chloride reacting with barium hydroxide to make sodium hydroxide and barium chloride. Now, this equation is not currently balanced, but with just a little bit of manipulation, we can balance it pretty easily. So once again, we are looking just for the net ionic equation. So classify it, break it apart, and cut out all the common things to get to the net. right. It gets tough sometimes when we start throwing in those acids and bases and trying to figure out what to do with them. That's why we have to stick to our classification system to try to help us out. So what do we know about sodium chloride? How would we classify it? Yeah. Even if you knew nothing of the solubility rules, sodium chloride's table salt, we know it dissolves in water. What about barium hydroxide? Okay. We know it's a base. It's a base because of the hydroxide. What kind of a base is it? Where is barium? Barium's in group 2. It's below calcium. It's a strong base. Similarly, hydroxide and sodium hydroxide. We know it's a base. Where is sodium? Sodium's in group 1. All of the group 1 bases are strong. So it's a strong base also. Now we come to barium chloride. Now, barium has no specific solubility rule. Chloride is soluble except for mercury, lead, silver. Barium's not one of those. So it's soluble also. So here's the thing that we have to be careful of. We have to be careful of assuming that because a chemical reaction is written, that we're going to get some sort of visible result. Walking around, I saw a lot of people classify barium chloride as insoluble. It's not. Barium chloride is in fact quite soluble in water. So as I go to the ionic here, this is soluble, so it breaks apart. Sodium ion, chloride ion. This is a strong base. All strong bases completely dissociate as well. Barium ion, 2 hydroxide ions. Sodium hydroxide, strong base. It completely breaks apart as well. Sodium ion, hydroxide ion. Barium chloride is soluble. Barium ion, chloride ions. So what we have in this instance is something kind of unique. I can see that the sodium ion is common on both sides. The chloride ion is common on both sides. The barium ion is common on both sides. The hydroxide ions are common on both sides. They all cancel out. So what's left? Nothing. There's no reaction here. Nothing changed. If nothing changes, then we have no reaction. So one of the kind of places where you can make mistakes in net ionic equations is assuming that a reaction has to occur because you've been given a chemical equation for it. The whole point of net ionic equations is to prove that reactions are actually taking place. Now, if you put those two substances together, you would see no evidence of a chemical reaction. This is different from, say, a neutralization reaction where we have an acid and a base coming together and we see no visible change, but we might see a change in temperature, or we might see a change in indicator indicating that the pH has moved around in some kind of way. We're not seeing any of that here. And our net ionic equation gives us kind of the ammunition to say definitively conclusively with proof that nothing actually happened. So try to stay out of that particular trap. The trap I'm talking about here is the trap of assuming that something is going to occur because we have a chemical equation that outlines it. Molecular equations can lie to you. They can let you know about things that aren't actually true. This looked like a perfectly viable chemical reaction. But the reality is, it's a recipe for a solution. The solution has nothing new in it. All right, any questions before we move off of net ionic equations? So the other main topic that we want to get into for today is redox reactions. Oxidation reduction reactions, otherwise known as redox, are paired reactions. They occur at the same time. And the processes are kind of like a large umbrella. So if we look at those 5 types of reactions that we did, we'll notice that 4 of them have tendencies to fall into oxidation reduction. The only one that really doesn't is the double replacement reaction, because the double replacement reaction, we know that none of the charges change. But in all of the others, there's usually something that is going on with those electrons. Those electrons are transferring from one element to another in some kind of way. For oxidation, we have a tendency to look for one of 2 things. Either we see an increase in oxygen for something, or more precisely, we see the loss of electrons in some kind of way. The thing about oxygen, it happens some of the time. It's a way that we can kind of visually inspect to see if oxidation has possibly occurred. Tracking the charge is the best way to do it. And so if we track charges, we will see that things that are oxidized have lost electrons along the way. Their individual charges get more positive. Reduction, on the other hand, we see one of 2 things occur. We either see a loss of oxygen. Again, that's not always a tried and true. That doesn't always happen, but it can be something we look for. Or, more commonly, we look for gains of electrons. We see charges getting more negative. Regardless of how we explore and look at oxidation and reduction, what we have to understand is that the 2 processes are paired. That's why they're called redox reactions or oxidation reduction reactions. You cannot have an oxidation without a reduction. Something can't just lose electrons and that be the end of it. Those electrons have to go somewhere. They have to be absorbed by something. And that's what gets reduced. So neither process happens isolated from the other. They both have to occur at the same time. Now, there are a couple of ways that we can think about this and try to keep it straight in our heads, because honestly, oxidation and reduction are very easy to get mixed up, especially if we start to look into ideas of like trying to figure out what is an oxidizing agent, what is a reducing agent, because those terms actually take on a meaning that seems counterintuitive sometimes. So there are two ways that we can use to try to keep it straight. The first is Leogar. Now, if we want to go back in the Wayback Chemistry machine for Dr. Bruck, Leogar is how I was taught. Leo the lion goes grr. Leo is the loss of electrons, is oxidation. Grr, the gain of electrons, is reduction. Leo the lion goes grr. So that's Leogar. Again, that's the way I was taught. Doesn't mean it's right. Doesn't mean it's the best. It's just the one that I've stuck with. Now, sometime when I was in college, someone introduced me to the idea of oil rig. It works as well. Oxidation is the loss of electrons, oil. Reduction is the gain of electrons, rig. Put them together, oil rig. Understanding that in both cases, the electrons lost go to the thing that gains them. They both have to occur at the same time. Now, the way that we monitor redox reactions, how we can determine that a redox reaction has occurred in the first place, is through something called an oxidation number. An oxidation number basically represents the current charge on a given element inside of a compound at any given time. So regardless of whether we are looking at an element as just itself an element, or as an ion, or in a larger compound, that element is going to have an oxidation state, an oxidation number, a particular charge on it. And based upon what that charge is, we can go a whole lot about how it's going to react. If it has a very high positive charge, the chances of it getting reduced and lowering that number increase significantly. If it has a large negative charge, the chances of it giving away some negative and becoming more positive also increase significantly. How do we assign oxidation numbers? Well, there are unfortunately no real good memorization tools that I can give you for this. But what I can give you are some guidelines and processes that will help. And the first guideline is this. If I take all of the oxidation numbers for all of the elements in a given compound and I add them all together, the sum of all of those oxidation numbers is going to equal the total charge on whatever it is that I'm studying. So for example, if I have the chromate ion, CrO4 negative 2, what that means is that the charge on the chromium plus the charge on the 4 oxygens has to equal a total of negative 2. The other thing to know is that all of these oxygens are all going to have the same number. In that case, in this particular case, it's negative 2. We'll get into the why here on the next slide. So with that information, I can look at this and say, okay, well, if the chromium plus those 4 oxygens is negative 2, and I know each oxygen is negative 2, the only logical way to solve this problem is that chromium has to be positive 6. So I can use this idea to help solve for oxidation numbers if I know a little bit of information. Now, what it also means is that if I have an atom that is just in its own element, or part of a molecular elemental substance. So I've got sulfur as an atom. It's uncharged. Its oxidation state 0. If I have sulfur in S8, the 8-membered ring, that sulfur often comes in terms of its allotrope. Each one of those sulfurs has no charge. It's a 0 oxidation state. If I have chlorine, chlorine as an atom, 0. Molecular chlorine, Cl2, also 0. So if I have an element by itself, it's going to take on whatever the charge is. If it's uncharged, if it's neutral, then every single one of those atoms is 0. If it is a monatomic ion, like the chloride ion, it'll just take on its normal charge. So chloride being a halogen, -1 charge is expected. That's its oxidation state as well. So if I have elements by themselves, their oxidation state is 0. If I have ions by themselves, single atom ions, the charge on that ion is its oxidation state. So that's the first guideline. The second guideline has to do with common states. So there are certain substances, certain elements that because they are highly electronegative, meaning they draw electrons to themselves very, very, very well, because of that, they have a tendency to have common charges. Fluorine. Fluorine as an element would still be 0. But if I have fluorine in any kind of compound, whether it's ionic or covalent, it's going to take on a -1 charge. Why a -1 charge? Because fluorine is the most electronegative element on the periodic table, and it's going to draw electrons to itself always. And its most common charge, because it is a halogen, is -1. So that's the charge it's going to take on. Hydrogen. Hydrogen, we know element number 1. Hydrogen really only has 3 possible oxidation states because it is in that first energy level. It can have the 0 state when it's by itself. It can have its most common +1 state where it gets rid of that electron when it pairs up with other nonmetals, which is usually what it does. Or if it pairs up with something that's more metallic than it, it can add an electron, take on the configuration of helium, and be -1. Those are the only 3 options for hydrogen. By itself, it's 0. With a nonmetal, it's positive. With a metal, it's negative. Those are its only options. And finally, oxygen. Oxygen's oxidation state is usually -2. Oxygen is the second most electronegative element on the periodic table. And its most common charge, since it's in group 16, is -2. However, when it's by itself, it's going to be 0. And if it were ever with fluorine, the fluorine's -1 is going to take precedence. The only other exception is if I have a peroxide, that -2 charge on the peroxide gets distributed over both oxygens. So each one only has a -1 charge instead of a -2. But again, those exceptions are relatively rare. Most of the time, if we see oxygen, we can say -2. Very rare occasions, it would be anything else. So let's do some practice with this. What are the oxidation states of sulfur in S8, sulfur dioxide, sodium sulfide, and calcium sulfate? So we start with the first one. S8, this is the same thing as sulfur by itself. There's only sulfur in this compound. Mathematically, we could kind of work it this way. 8 times the sulfur is equal to the overall charge of 0. 0 divided by 8 is still 0. Sulfur has no charge. Again, anytime we have an element by itself, even if it's in a molecule, so long as the only element there is sulfur in this case, they're all going to be zeros. So all 8 of those sulfurs have no charge. Let's look at letter B, sulfur dioxide. Now again, with sulfur dioxide, we see that there is no charge overall on the sulfur dioxide. So if I'm setting up my algebra, I've got sulfur and I've got 2 oxygens. Total charge on the whole thing is 0. It's an uncharged molecule. From our previous guideline, guideline number 2, we know that oxygen is usually -2. This isn't one of those exceptions. It's not oxygen in its elemental form. It's not a peroxide. So it's -2. So sulfur plus 2 -2s is equal to 0. 2 times -2 is -4. So sulfur has to be a +4. The +4 of sulfur cancels out the -2s of the oxygen. So one of the hardest things to kind of wrap your brain around when it comes to oxidation states is recognizing that when we're dealing with something that is not particularly electronegative, paired with things that are, they're not going to take on their normal charges. So your first instinct might have been, okay, sulfur and oxygen, they're both in group 16. They should all have -2 charges. Problem is, that's not how it works. In molecular compounds, it's all about electronegativity. The closer you are to fluorine, the more electronegative you are. The more likely you are to carry your normal charge. And so if you aren't the most electronegative element, that other element is more or less going to take your charge from you. All right, let's look at letter C. Letter C, we have sodium sulfide. When we have ionic compounds like this, what we need to do is break them apart into their ions and evaluate each ion individually. So sodium sulfide, I've got the sodium ion and I've got the sulfide ion. Since those are both monatomic elements, monatomic ions, their charge is their oxidation state. So the sodium's +1, the sulfide is -2. In this case, it really is just as easy as it looks. It's the periodic table. And when we have binary compounds like that, that's exactly what happens. Finally, for letter D, calcium sulfate, we need to do the same thing. We got to split the calcium from the sulfate. So the calcium is a +2. The sulfate is a -2. Now we need to do that evaluation. Sulfur plus 4 oxygens is equal to -2. If each oxygen is -2, then sulfur must be a +6. Now, if that looks a little bit familiar to you, it's basically the same breakdown that we did for the chromate ion a couple of slides ago. One thing that you will notice is that there are going to be some patterns that kind of emerge. If I have an element with 3 oxygens, here's what the oxidation state looks like. If I have an element with 4 oxygens, here's what the oxidation state looks like. There's going to be some common threads there. So that's not necessarily a memorization tool, but just kind of recognizing that there are patterns and we can take advantage of those patterns. So if I know the oxidation state of chlorine in chlorate, the same oxidation state will be there for bromine in bromate, iodine for iodate. Because the breakdown of the ion is the same. I've got a halogen and 3 oxygens making a -1 charge. So it doesn't matter what the halogen is. 3 oxygens are going to make a -6, which means that the halogen is going to be +5 to give the -1 overall charge. All right. We're going to actually leave this one alone. I want to talk about one other thing. We haven't talked about oxidation reduction reactions yet. What we need to understand is that when these reactions occur, when we see this transfer taking place, there are names that we can associate with the reactants themselves. So a reducing agent is a reactant that forces reduction. And an oxidizing agent is a reactant that forces oxidation. So in this reaction, we have zinc, which has no charge, turning into zinc with a +2 charge. We can see that the copper, which had a +2 charge, is losing that charge. The zinc metal, we would refer to that as a reducing agent. It is forcing the copper 2+ to gain electrons and become copper 0. The copper 2+ we can refer to as an oxidizing agent. It is forcing the zinc to give up its electrons to the copper. Now, I'm going to make a decision here, and that decision is to actually hold up on I'm going to push this assignment to Friday. Give us Friday's lecture. We're going to need maybe 15, 20 minutes just to kind of review and recap. If you're feeling pretty good right now, go ahead and take a crack at it and try it out. If not, after Friday's lecture, we'll certainly be in a better place. And you can try it that evening. So that's all I've got for today. If you're able to come this afternoon, really appreciate it. Otherwise, have a good afternoon. I'll see you.